Hello, chemistry students. Today we're going to be talking about acid-base neutralization reactions. And these are a type of double replacement reaction. So if you need a refresher on that, I recommend go watching the video I made on double replacement reactions. So in this case, we're going to be looking at very specific types of ionic compounds being involved in the double replacement. The first is an acid, which is a ionic compound that has hydrogen as a cation. Hydrogen being in the first column on the periodic table is going to have a +1 charge. So that's going to determine the types of ionic compounds it can make. So we see HCl, HBr. A lot of acids have fancy names like hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, nitric acid, sulfuric acid, phosphoric acid. But you don't necessarily need to call them by those names. You can also just refer to them as like hydrogen chloride, hydrogen bromide, hydrogen iodide, the main way that we've been referring to ionic compounds in the past. And a base is classified as an ionic compound that has hydroxide as the anion. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, etc. And these don't really have any fancy names. You can just use the normal ionic compound name for them. So acids and bases, you might know from just media, are usually really corrosive, but that's mainly in very high concentrations with really high doses of those acids and bases. But in general, lots of acids and bases are found in household products and food products, but usually in safe to use or safe to consume proportions. Um, a pH is a normal measurement that's used to determine if something is acidic or basic. And we might talk a little bit more later about what that means. But acids usually have a pH of below 7, and bases usually have a pH of above 7. And water, which is considered to be neutral on the acid-base scale, has a pH of exactly 7. So all of these things that are below 7 here, this like milk, bananas, stomach acid, lemons, these are all considered to be acidic, and things like soap, ammonia, bleach, lots of cleaning products are basic. Um, but let's talk about how these types of chemicals react with each other. So like I mentioned before, this is a double replacement reaction. So we're going to be using the same mechanics that we used previously for this. And let's consider the reaction between hydrochloric acid or hydrogen chloride, HCl, and sodium hydroxide, NaOH. So much like double replacement reactions, we're going to have our cations and our anions switch places. So the hydrogen is going to go with the hydroxide and the sodium is going to go with the chloride. So we're going to end up with NaCl because it's a +1 -1 charge. And then we're going to end up with HOH. And you'll notice I put L here, which represents liquid, because if you think about what this means, HOH, that's two hydrogens and an oxygen, that's just H2O. That's water. So the key difference between the double replacement reactions that we looked at before, where we were making precipitates, and acid-base neutralization reactions, are in these you form water, which we mentioned earlier is a neutral compound. That's why we call them neutralization reactions, because the acid and the base are sort of canceling each other out. So when you're writing out the chemical equation, it's okay to write it as HOH at first, especially when you're trying to balance it and make sure that all of the ions are in the same proportions on both the reactant side and the product side. But eventually you're going to want to replace the HOH with H2O at the end to really show that you know that this is water being formed in the process. So let's do, and another note, we call it liquid and not aqueous because aqueous usually implies that something is dissolved in water, and water cannot be dissolved in itself. Water is water, so we just write pure liquid water at the end, or as the state of matter for the H2O. All right, let's try an example. So here we have potassium hydroxide, KOH, reacting with phosphoric acid or hydrogen phosphate. And much like before, we're going to have our cations and our anions switch places. So our potassium is going to go with our phosphate, and our hydrogen is going to go with our hydroxide again. And you see that's going to be a pattern. We're always going to have hydrogen and hydroxide combining to make water in these acid-base reactions. So we end up with potassium phosphate. So potassium has a +1 charge, phosphate has a 3- charge, so we're going to need 3 potassiums for every 1 phosphate. And then we're going to form 3 HOHs because we needed 3 potassium hydroxides to get enough potassiums to combined with the phosphate, and there was 3 hydrogens on the phosphoric acid, so we needed 3 hydroxides to neutralize all of those. So we ended up with 3 HOHs, which is going to be liquid, and we're going to change it to H2O at the end. So we have a more clear idea that this is water at the end. Another interesting thing to determine for acid-base neutralization reactions is the net ionic equation. So let's show how we do that again. First, we get the total ionic equation. So we split up all of the aqueous compounds. So we have our potassium and our hydroxide splitting up. We have our hydrogen and our phosphate splitting up. Here we have potassium and phosphate splitting up. And you'll notice here that I kept the water together. Since it's liquid, since it's not a aqueous ionic substance, the HOH is not split up. So we keep the water together, much like we would a precipitate in a precipitation double replacement reaction. So much like before in our total ionic equation, we're going to cancel out all of our spectator ions. So the potassium goes away and the phosphate goes away. And we're left with 3 hydroxides, 3 hydrogen ions, making 3 waters. And since this is a 3 to 3 to 3 ratio, which is just a 1 to 1 to 1 ratio, we're going to reduce that down, and we end up with hydroxide ion plus hydrogen ion making water. And if you're doing this correctly, the net ionic equation for all of these acid-base reactions is going to be exactly the same. You're always going to end up with hydroxide and hydrogen combining to make water, because that's kind of the key idea here, is that acids and bases neutralize each other. In a chemistry lab, anytime there's like a big acid spill, you're always going to want to take some sort of a base powder and add it to it in order to neutralize it so that the corrosive acid gets neutralized and can't corrode anything or hurt anybody. Acids and bases are always able to neutralize each other if they are added together in the right proportions, because they'll always just form water in the end when they're combined. All right, let's do one more example. So let's try to predict the products and balance the equation for the reaction between ammonium hydroxide, which is going to be a base since we know it has a hydroxide as an anion, and carbonic acid, otherwise known as hydrogen carbonate. So first let's write out our reactants. So we're going to have NH4OH, that's our ammonium hydroxide, and then our carbonic acid / our hydrogen carbonate is going to have this formula. Carbonate has a 2- charge as a polyatomic, so we're going to need 2 hydrogens to cancel it out. And these 2 hydrogens are going to want to combine with hydroxide, so we're going to need 2 of those. And then the ammonium is going to combine with the carbonate, and we're going to need 2 of those anyways, because this has a +1 charge, and that has a 2- charge, so we're going to want to add a 2 in front of there when we balance it. And we're going to end up with ammonium carbonate, which is going to be aqueous based off of our solubility rules, because we know that ammonium compounds are always soluble. And then we're going to form 2 HOH, which we then turn into H2O. And that's going to be our balanced chemical equation for this acid-base neutralization reaction. So that is all I have to say on this topic, and I'll see you in the next video.